So in this lesson, we're going to start out with section 6.4, which is Cramer's rule. But before we do that, we get a theorem here to get us started, and that is that if we start with an n by n matrix A, that it will be non-singular. In other words, the column vectors will be linearly independent if and only if the determinant of A is non-zero. So this is a nice way for us to test for being singular or non-singular for a particular matrix, and also to test whether or not a set of vectors is linearly independent or dependent. We can use this as well by throwing that into a matrix and then checking its determinant value. So it gives us an alternative to that. As sort of a proof of part of this, we have the following. We'll start out with the assumption that A is in fact non-singular. So since A is non-singular, we know then that A inverse exists. And as a result of that, of course, then A inverse times A would be equal to the identity matrix. We can then take the determinant of A times A inverse. And using properties of matrices, this becomes the determinant of A times the determinant of A inverse. Again, this is going to be equal to I by our earlier statement. And that would then imply that the determinant of A is equal to 1 over the determinant of A inverse. Which means that the determinant of A has to be non-zero, because there's no way to make that zero. And again, that started with the assumption that A was non-singular, and we showed then that if it's non-singular, the result must be that the determinant of A is non-zero. So again, non-singular here, meaning the determinant is non-zero. So we proved that section of it. We can reverse this whole argument, and that's where this if and only if statement comes from. It means that the argument is reversible. So if the determinant's non-zero, that means A is non-singular. And that's generally how we use this particular result. And I guess it's maybe worth noting one additional part on this, and that is that this would also imply that the determinant of A inverse is equal to 1 over the determinant of A. I don't know that's a particularly useful result, but it is in fact a result nonetheless. So like I said, this gives us another way to show linear independence or dependence. So the way we could do this then would be to grab some vectors maybe. So let's take some vectors like 3, 1, 4, and we'll take another ones 1, 1, 1, and 1, 0, 0. And in all likelihood, these would be linearly independent. And we'll verify that by throwing these into a matrix and then finding its determinant.